Only days after Typhoon Fong Wong tore through the Philippines, reducing entire provinces to flooded plains and pushing more than 1.3 million people into desperate evacuation shelters, a new alarm begins to rise from beneath the soaked and fractured ground. An alarm so severe that even the country's most seasoned seismologists struggle to accept what the instruments are showing. The nation is still reeling. 482,614 displaced residents sleeping on plastic mats, families huddled in school gyms with no power, and whole towns in Cagayan Valley drowned under nearly 12 meters of surging river water. Yet, as the last torrents recede, a different kind of storm begins to unfold in the silence before dawn. At 2:13 a.m., seismic stations across Luzon record a sudden, violent shift, pressure signatures that do not belong to the gentle aftershocks of a passing typhoon, but to something deeper, heavier, and infinitely more dangerous. Analysts watching the live feeds freeze, unsure whether the jagged spikes on their screens are glitches or the first tremors of a system reaching its breaking point. Outside, families do not hear the sensors screaming, but they feel the ground pulse beneath the soaked debris of collapsed homes. This is the moment that should not exist. A country brutally weakened by a megastorm now standing on the edge of a potential 9.0 megaquake, a scenario so improbable that no forecast model, no geological briefing, no emergency protocol had ever fully accounted for it. The question forming in every control room, whispered with the weight of dread, is one no one wants to ask out loud. Is Typhoon Fong Wong merely a catastrophe or the trigger for something far worse? For decades, the stability of the Philippine mobile belt has been explained through rules as old as plate tectonics itself, rules that have governed the rise of mountains, the birth of trenches, and the release of seismic energy long before modern instruments existed. Under normal circumstances, the Sunda plate subducts beneath Luzon at a steady rate of up to 100 millimeters per year, a glacial creep comparable to the speed at which fingernails grow, except multiplied by billions of tons of rock grinding at the boundary of the Manila Trench. This trench, often mistaken for a single linear scar, is actually a fractured system split into northern, central, and southern segments, each with its own tempo of motion and its own history of rupture. Locked deep along these segments are the infamous asperities, patches where the plates refuse to slip, where stress accumulates silently over centuries. Geological records show that the largest earthquakes in this region recur every 400 to 900 years, a reminder that the countdown to disaster does not follow human calendars. In the atmospheric world, the rules are equally defined. Late-season typhoons almost always weaken over cooler waters. Storms rarely sustain destructive power this far into November, and rainfall, no matter how intense, should not influence tectonic plates lying tens of kilometers beneath the surface. These principles have shaped every forecast model used to understand the region's risks, but this year, the rules are falling apart. Typhoon Fong Wong, a storm that should have died in the South China Sea, not only intensified, but delivered an unprecedented load of more than 10 billion tons of water directly onto one of the world's most complex fault networks. Instead of dissipating like every November storm before it, it drenched an already saturated landscape, striking at precisely the wrong moment, when multiple trench segments were showing signs of tight coupling and rising strain. The contradiction is impossible to ignore. The laws of nature insist that storms do not trigger megaquakes, yet the data emerging from Luzon suggests that something fundamental has shifted. And as these long-trusted rules begin to unravel, a darker question takes shape. If nature is breaking its own limits, why now? At 2:13 a.m., just hours after Typhoon Fong Wong's final rain bands drifted away from Luzon, a sharp pressure spike erupted across deep Earth sensors near the Sierra Fault region, instantly triggering internal red alerts at FIVOLCS headquarters. Within minutes, seismic dashboards from Aurora, Quezon, and central Luzon lit up with clusters of microquakes. Over 200 tremors in just 36 hours, nearly triple the pre-storm baseline. Individually, they were small, between M2 and M4, but together they formed a pattern that seismologists dread. A swarm showing the same spatial and temporal rhythm recorded before the 2011 Tohoku Megaquake and the 2004 Sumatra rupture, two of the most devastating earthquakes ever documented. Engineers reran their algorithms a dozen times, searching for glitches. None appeared. Instead, new anomalies surfaced. Borehole sensors showed fluid pressure rising to unprecedented levels, the kind associated with deep pore pressure modulation, an effect seen when massive surface loads push water into fractures below. Then came the satellite confirmation. Grace data revealed a staggering 10 to 20 gigatons of added mass across multiple basins, translating into surface loading stresses up to 4 kilopascals, a figure more commonly associated with post-glacial rebound models than a single typhoon. Meanwhile, GPS velocity fields displayed sharp gradients along the Luzon block, accelerating northwest at 65 millimeters per year, while the Visayan and Mindanao microplates rotated in opposing motions, tightening strain along the Manila Trench's northern and central segments, the very segments already identified as strongly coupled asperities capable of producing a magnitude 9 class rupture. Inside FIVOL-CS, a leaked memo, its subject line reading, "Situation escalated, pressures at record highs," circulated among analysts. The document warned that the 10 billion ton water load from Fong Wong had pushed stress levels on several trench segments into uncharted territory. During an emergency briefing, Dr. Maria Evangelista cut through the jargon with a single line. "The pressure curves we are seeing look eerily like the ones before history's biggest earthquakes. This is not normal post-storm noise." Her statement echoed those of Dr. Irene Pascual, who argued that the system was already near its breaking point and that the storm acted as the final straw. Skeptics pointed to subduction forces measured in hundreds of megapascals, insisting a few kilopascals of rainfall-induced stress could not produce a megaquake. But as borehole pressure climbed, microquake clusters intensified, and satellite anomalies persisted, their objections rang increasingly hollow. 4 independent systems, ground sensors, borehole monitors, GPS arrays, and orbital satellites, were now telling the same impossible story. And when that happens, the problem is not the equipment, the problem is the Earth. Across the battered landscapes of Luzon and the Visayas, the human cost of Typhoon Fong Wong lingers in every flooded street, every collapsed roof, every gymnasium turned shelter where more than 1 million evacuees fight exhaustion on thin plastic mats. In Cagayan Valley, where the river rose nearly 12 meters and swallowed entire neighborhoods, families cling to relief packs as rumors of strange tremors ripple through the crowded halls. The official count lists 482,614 people driven from their homes, but on the ground, the real number feels far higher, an ocean of displaced lives trying to steady themselves just as the earth begins to tremble beneath them. For those outside the shelters, the fear comes not from headlines, but from sensation. Faint pulses under the mud, small cracks widening across village roads, and the unsettling memory of aftershocks that followed previous disasters. While civilians grapple with survival, the scientific front lines face a different kind of pressure. Inside FIVOL-CS control rooms, Dr. Maria Evangelista monitors jagged pressure curves blinking in red, data she has called eerily similar to pre-Tohoku patterns. Meanwhile, in the tense halls of the University of the Philippines, Dr. Irene Pascual and Dr. John Power argue over rainfall mass anomalies and borehole pressure spikes. Pascual insisting that 10 to 20 gigatons of stormwater added the critical stress needed to tip locked segments of the Manila Trench, power countering that rainfall cannot override hundreds of megapascals of tectonic forces. The debate is sharp, but overshadowed by what both sides silently acknowledge. The system is behaving in ways none of them can fully explain. On the engineering side, Felipe Rodriguez reviews damage reports from rapid assessment teams. Bridges in Mabini, Jones, and Ayala show fresh scouring and cracks. If shaking begins, he warns, these spans won't last, and once they fail, evacuation routes vanish. Telecom engineers add another layer of urgency. Cables running beneath rivers and crossing the Manila Trench are already strained from storm damage. A rupture could sever communications across Metro Manila and western Luzon for weeks. Deep inside Malacañang Palace, policymakers wrestle with decisions none of them feel ready to make. One memo urges immediate warnings and infrastructure shutdowns. Another warns that triggering panic during the Apex summit could destabilize the nation further. The clock is ticking, and every faction knows it. For the millions huddled in shelters, the technical battles are invisible. But for the scientists and engineers parsing each tremor, each rising pore pressure reading, the crisis is unfolding in real time. And in this fragile moment, between the storm that already destroyed so much and the quake that may follow, data is no longer academic. It is the thin line determining who escapes and who does not. Inside the stark fluorescent corridors of FIVOLX and the dim, crowded briefing rooms of Malacañang Palace, a quiet but escalating conflict erupts, not between nations, but between interpretations of the truth. As microquake swarms continue to flare beneath Luzon, two scientific camps form a fault line of their own. One faction, led by Dr. Irene Pascual, argues that the combination of 10 to 20 gigatons of stormwater mass, record-breaking pore pressure spikes, and the activation of multiple locked asperities along the Manila Trench represents a dangerous and unprecedented alignment. Their stance is blunt. The system is already critically loaded, and even a small nudge may be enough to unseal centuries of accumulated strain. The opposing camp, represented by Dr. John Power and a group of senior analysts, urges caution. They warn that rainfall-induced stress typically measures only a few kilopascals, insignificant when compared to the hundreds of megapascals generated by tectonic forces. Power reminds the committee that past studies from Japan and New Zealand show rainfall triggering landslides and minor faults, not magnitude 9 megathrust ruptures. But the problem is not that one side is right and the other is wrong. The problem is that both sides possess only fragments of a puzzle that is shifting faster than their models can compute. Fueling the tension are a series of confidential memos, some leaked, others whispered in back-channel threads. A technical bulletin from the Department of Public Works and Highways warns that bridges in Mabini, Jones, and Ayala could fail with even moderate shaking. A document from a telecom watchdog group raises alarm that fiber optic cables running beneath the Manila Trench and across swollen rivers are at risk of snapping, potentially isolating Metro Manila and Western Luzon during the first minutes of a major event. Meanwhile, a memo circulated by the Office of Civil Defense urges restraint, claiming that issuing mass evacuation orders so soon after Typhoon Fong Wong and during the high-stakes Apex summit could trigger national panic and undermine international confidence. These contradictory directives force policymakers into a corner. If they warn the public too early, they risk chaos. If they warn too late, they risk catastrophe. And as seismic alerts accumulate and flood-soaked infrastructure weakens, the margin for error narrows to nothing. In the end, the Earth does not pause for debate, nor wait for experts to achieve consensus. It does not care about memos, optics, or political timing, and it will not delay its next move until humans agree on what the data means. Across the wider map of the Pacific Ring of Fire, The warnings coming out of the Philippines and Taiwan no longer look like isolated anomalies. They look like the early contours of a new geological and atmospheric era, one where the boundaries separating climate and tectonics begin to blur. As Typhoon Fong Wong swept across the region, it behaved in ways that defied every rule meteorologists trusted, forming late in November, strengthening over waters that should have cooled, striking from the southwest instead of the east, and delivering rainfall so extreme that Suao recorded the most precipitation in Taiwan's history, with 25 inches falling in a single day. More than 8,300 people fled their homes, 1,000 houses were left underwater, and 15 residents were injured as the storm carved a path that none of the traditional models, ECMWF, GFS, JMMA, or the CWA's high-resolution systems could accurately predict. Forecast runs projected weakening. Satellite images showed intensification. Statistical probabilities insisted such a storm should not exist. Yet it did. At the same time, the Philippines, already pummeled by Fong Wong's unprecedented weight of 10 to 20 gigatons of water, now faces a fault system showing the kind of synchronized agitation typically seen only before history-shaping catastrophes. This convergence, a storm rewriting the laws of meteorology and a trench exhibiting strain signatures outside known parameters, points toward a broader shift, a world where extreme weather no longer stops at the surface, where rainfall alters pore pressures at depth, where saturated soil accelerates landslide risk, where atmospheric anomalies coincide with geological ones, and where the old assumption that storms and earthquakes are unrelated begins to erode under the weight of real-world evidence. Scientists across Taipei, Manila, and research institutes from Japan to New Zealand are now quietly exploring a possibility once dismissed as fringe, that in hypercharged climates, intense storms may modulate stress in already loaded fault systems, acting not as the cause of megaquakes, but as the final destabilizing force. For millions of people living along the Ring of Fire, this is the new reality, one where the next disaster may not wait for seasons, cycles, or predictions, and where the planet's most violent forces may emerge from the overlap of sky and stone. And if what we are witnessing now is only the beginning, then the truth may be far more unsettling than anyone is prepared to admit. If this is the beginning, imagine what comes next.